Okay. Okay. So today we previously we learned the dispersion, right? So again, I'll use this chart, right? This chart. What we have is 0 t u tilde 0 omega, and then use z omega, right? And then use z t. Right? So we first take the Fourier transform. Then we propagate. We'll propagate exponential I k naught double prime z, right? Exponential I k naught double prime z, and then we have this Fourier transform back. Right? So so that's the main mechanism. So we did this both in analytical method, right? We assume it's Gaussian function. We assume it's Gaussian function, and then we can solve it analytically. In addition, in the homework, we also solve different secant, right? Secant, which is difficult for Fourier transform, right? Secant and the super Gaussian. So in this case, we can use this numerical method, right? Numerical method, we can do the same thing, Fourier transform and the exponential I k naught double prime omega square z, and then Fourier transform back, right? So for the Gaussian parts, which can be done by analytical method, we show the agreement between our analytical method and numerical method, right? And for the rest, so the secant parts and the super Gaussian, we just use our numerical MATLAB code, right? So you should see the difference where they broadening, and you should explain why, right? You should explain why. You need to look at which one has broader spectrum, so it will have more impact from the dispersion effect, right? Okay, today we'll go start a new material. It's called third order dispersion. So basically, we previously we look at the low order dispersion. Today we'll look at the higher order dispersion. So it's higher order effect. So it's third order dispersion. Right, third order dispersion effect. This pen is going bad. I'm using a new pen. So it's the third order dispersion. Right? Okay. So let's first review the Fourier transform. Right? What happened in the Fourier transform? We have the hold on. Okay. This is actually bad neither. Okay. So, but let's try it. Right. So it's U. Kind of bad today, picking up wrong pen. Okay. Hopefully the rest will be good. Oh yeah, this is much better. Okay. So it's the third order dispersion. First, let's look at U tilde omega is negative infinity infinity ut exponential I omega t dt, right? That's the Fourier transform. This is the Fourier transform. Okay, then the inverse Fourier transform ut is what we have as the 1/2 pi negative infinity infinity omega tilde u tilde omega exponential negative omega t d omega, right? So this is the u omega and ut, right? Okay, then for this case, we can take a derivative, dut dt, right? Take a derivative with respect to t, and this integral is an integral over omega, right? So let's take a derivative. The only component has a t, is this exponential negative omega t, right? So in this case, we'll just move down the negative omega, negative infinity to infinity, negative I omega, and then u tilde omega, exponential negative I omega t d omega, right? Okay, please feel free to interrupt me if you have any question. So this is just a review of Fourier transform, which will be used later, right? We can further take additional derivative with respect to t, right? Square second derivative is the derivative of the first derivative, right? So 2 pi negative infinity infinity, and then we have another negative I omega falling down, right? I always call it another negative I omega falling down, right? U omega tilde exponential negative I omega t d omega, right? So with that, we can see the Fourier transform pair, right? We can actually mark the Fourier transform pair in the sense that this piece is the Fourier transform pair of this piece, right? Because those two, they are the Fourier transform pair. And this component and that component, they are the Fourier transform pair, right? Fourier transform pair, and this is the Fourier transform pair, right? Okay, so with that, we can rewrite it in the form that those two du dt, the Fourier transform is the negative I omega u tilde omega, right? If the ut and u omega is the Fourier transform pair, then our du dt and negative I omega and u tilde m omega is also a Fourier transform pair, right? Okay, so now we can rewrite another equation. So this would be du dt second derivative. The Fourier transform pair is going to be negative I omega square u tilde omega, right? It's going to be the negative I omega square u tilde omega. So each of the derivative in time domain corresponding to an additional factor negative I omega in front of u omega, right? So that's what we learned in the beginning of the class. Since we are going to use it here again, so let me actually write down the equation again, right? Okay, so we're good. So now let's look at the back. So the previously we did a lot of derivation, and we reached an equation partial u partial z u zt, right? And the minus k naught double prime over 2 partial u partial t square and zt, right? And that's the second derivative. And then minus I over 6 k naught triple prime partial u partial t, right? Cube and cube, right? Zt equals 0. So now in this case, we previously obtained this equation, right? Previously obtained this equation. There was a first order derivative, but we know that this is just fundamental wave propagation. We actually change it. We changed the parameter, so it was included, right? So it was included. So in this case, we only list the second derivative and third derivative. right? We only list the second derivative and third derivative. Okay. So previously, in previous case, what we did, all what we did last class is the piece including the d dz and d dt square. This term was not included. This term was not included. Today, we are going to include this third order term. Let's see how this third order term play a role in our dispersion, right? In our dispersion, effect. So let's take a Fourier transform, right? Fourier transform, right? Take a Fourier transform. In the first piece, we will have the I du tilde z omega, right? dz. So this is simply z propagation. So if we take a Fourier transform, it is simply change from u to ut to u omega, right? Now for the second case, we have the now we have du dt square, right? Second derivative corresponding to the negative I omega square u omega, right? So we should write it on, let's move to the right hand side. So it's become positive k naught double prime over 2. And then this is negative I omega square, and u z omega tilde, right? Remember du dt, the Fourier transform is negative I omega u tilde. Du dt second derivative is negative I omega square u omega, u tilde omega, tilde, right? U tilde omega, we add the z component here. Okay. Okay. Now let's look at the second term, right? Which is the third order. We move to the right hand side, become positive. So we plus I over 6, right? And then k now triple prime. That's the third order. And then this is the third derivative. Third derivative, I didn't write it. I should have write it actually. So let's write du dt cube Fourier transform. It's the negative I omega cube u omega, right? Okay, so then we will, what we have is we will get the third order. So it's plus of negative I omega third u z omega, right? U z omega, and that's the third. Yeah. Okay. Can we have a? I need to get a cup of water. So let's have a. Let's hold on for. Okay, great. Thanks for waiting. Okay, so now we have the second order dispersion, third order dispersion, right? Second order dispersion, third order dispersion. We can tell that all the previous work, homework 2, involved just simply the first piece, the one term on the right hand side. Now we need to involve the second term, which is the k naught triple prime in our equation on the right hand side. Right. Okay, so now we'll do the same, right? So I'll do the same steps. I will do the same steps on the right hand side We'll move the du dz move to the left hand side, dz on the right hand side. It's the same step with as what we did for the second order dispersion, but I'll just follow again. So that will be a review of solving this equation, right? So it's partial u z omega, right? Then it's partial, this will be, it will be u z omega, right? Equals on the right hand side. So it's the square of negative I omega. This will be the negative. There will be -1. Let's multiply negative omega on both left and right hand side. So it's become positive omega, positive I, right? Positive I over 2 k naught double prime. Then we get omega square, right? And then let's add the last second term, negative I cube, right? It's negative I cube. So it becomes I, right? Negative I cube. And so it will be an I, right? I and I will be negative, and we have a negative I, so it's positive I. So it's a lot of I's, right? So the 3I, 4, and 5. So at the end, it's the I. So you can solve that, k naught triple prime over 6 k naught triple prime, right? Why it's 6? It's 3 factorial, right? 3 factorial. Okay, and then it's the omega cube dz, right? So that's, I move the uz omega to the left hand side, and then move the dz on the right hand side. And then I'll take an integral, right? Take an integral. Here, this is the nature log, right? So it's nature log, then it's z omega integrate from 0 to z. I'm using the same parameter, just for simple case, right? Okay, on the right hand side, it's just simply z, right? So I over 2 k naught double prime omega square z plus I over 6 k naught triple prime omega cube z, right? Okay. Okay. So with that, we will have the nature log u tilde, right? So nature log u tilde, the solution will be nature log z omega over 0 omega, right? So now let's take a inverse, let's take an exponential on both left and right hand side, and then move the u0 omega to the right hand side. So let me step by step then. Z omega over u0 omega. So that is the exponential bunch of terms I'm just copying down, right? Plus I over 6 k naught triple prime omega square z, right? Okay, that's all the terms, right? That's all the terms. Okay, so at the end, what we have is the z0 omega equals u0 omega times the exponential, this big piece, right? Let me write it down, k naught double prime omega square z plus I over 6 k naught triple prime omega square z, right? Okay. Now remember, right? So you sounds familiar, right? This term looks familiar, right? uz omega is u0 omega exponential I over 2 k naught double prime omega square z. This is the component we just solved for the second order, right? For the second order, this piece, right? That's this step here. Now we want to add the third order. So it's just simple additional terms. It's just simple additional terms, right? So let me write down the whole equation, right? The whole equation. So the next step, what should we do? After taking the propagation, what should we do? inverse Fourier transform, right? So we did the Fourier transform, and what next is the inverse Fourier transform, which we will have is 0t as negative infinity to infinity u tilde z omega, but we need to multiply, right? So in this step, once we have that, we need to multiply back. What is z omega? So it's the 0 omega, right? So let me 0 omega times the exponential I over 2 k naught double prime omega square z plus I over 6 k naught triple prime omega cube z, right? And then we have exponential, and then we need to add another term is the Fourier transform minus I omega t, right? D omega. This is the exponential negative I omega t. So this piece, that piece up to here is the uz omega, right? And then we multiply by this piece is exponential negative I omega t, right? So we add them together, become the inverse Fourier transform, get back to the zt, right? Okay, now that's what we have here, right? That's what we have here. Okay. So next we will what we have is to use this in our code, right? So doing this is rather more complicated in analytical method. So next step, your job in the next homework, next lab session, instead of writing the factor as this piece, now your factor is this, right? So previously your factor, right? Your factor for the dispersion factor is this piece. Now your dispersion factor should include everything, right? So that's your lab session, next lab session. The next lab session, the factor is going to include the second order dispersion and also third order dispersion. This is your factor for the next lab session, right? Just include them, that's it, right? So include, but you need a k naught double triple prime parameter, which will be given hopefully. Okay, so we can do the same analysis, the LD, right? We did the LD, meaning that T naught over K naught double primes absolute value. Once the dispersion length, right? Once the Z is comparable to the dispersion length, then our pulse will be broadened, right? Remember, we have this pulse in your homework. So this is the Z equal to 0, and then this is the Z equal to 2LD. Then another one will be Z equal to 4LD, right? If the Z is far less than this LD, dispersion plays almost no role, right? They're almost the same shape. But once you have the LD, once you propagate 2LD, you have comparable, very distinct broadening, and 4LD is broadening too, right? So this is the dispersion length. This is the dispersion length. And one can do the same analysis. So I'll skip the steps, but just directly write down the LD prime is the T naught cube over K naught triple prime absolute value. and this is third order dispersion length. Third order dispersion length, right? Third order dispersion length. So with that, we can compare the impact of this dispersion, how at what circumstance dispersion, third order dispersion will play a role, right? At what circumstance third order dispersion will play a role. I got some allergy today. Okay, so let's look at this LD prime, right? So the LD prime, you can tell that this is T naught cube, right? This is T naught square. So it has a higher order effect, and also K naught triple prime. It's instead of K naught double prime, right? Okay, so third order dispersion, we can write as TOD. So it stands for third order dispersion, right? So third order dispersion effects play a significant role only if LD prime and LD. So do you think it's the LD prime greater than LD or less than LD? Yeah, so think about it. Do you think it's the greater than LD or less than LD? Okay. Any comments? Less than LD. Yeah. Okay, very good. So it's the less than LD, right? So I have a comment. It's the less than LD. Okay. So the reason is that this is the dispersion length, right? If the dispersion, third order dispersion length is way less than the dispersion length, that means I'm going to reach the dispersion, third order dispersion length first. I'm going to reach the third order dispersion length first. So once I reach the third order dispersion length, third order dispersion will play a role, and then before the second order dispersion play a role. So this plays a role significantly only if this third order dispersion is less than the second order dispersion, right? So and then let's write it down, right? So this will be the third order. So it's T naught triple prime. Oh no, that's not a T naught triple prime. It's a T naught square cube over K naught triple prime absolute value way less than T naught square over K naught double prime, right? Because it could be a different sign. Let's all take an absolute value, right? So T naught square cancel out. We move this K naught square on the left-hand side. So we have this K naught double prime over K naught triple prime, absolute value T naught far less than 1, right? This far less than 1. Okay, so I'm just writing down the condition, right? The condition that the third order dispersion will play a role. Because if you have LD, right? So if your LD, in the other case, the LD prime is way larger, greater than LD, then the mostly second order dispersion play an important role, right? Okay, so let's give an example. So if right? Example, we have 100 picosecond pulse, right? And my K naught K naught triple prime is 0.1 picosecond square over kilometer, right? And my K naught double prime needs to be, so if I make this condition, right? So I move the T naught on the over right hand side, K naught triple prime on the right hand side also. So this needs to be, which is the K naught double prime, needs to be way less than, right? So it needs to be way less than K naught triple prime over T naught, right? K naught triple prime over T naught. So in this case, what we have is going to be 0.001 picosecond square over kilometer, right? So it's the 0.1 divided by 100, right? So it's the 0.1. So if I have this condition, we have 100 picosecond pulse, K naught triple prime this, then my K naught double prime needs to be way less than 0.001 picosecond square kilometer, right? Okay, so it usually happen in this case, happen around zero dispersion wavelengths, lambda naught. So it is only occur or happen when this usually it's the second order dispersion is almost zero, right? Only occur mostly the second order dispersion is zero. So that's the condition when the third order dispersion will play a role, right? Okay, so that's what we first studied the second order dispersion. So mostly the second order dispersion play a role, but in some circumstances, the third order will dominate, right? But mostly the lower order will play a role. But occasionally you can find some special case that the third order will play a role. Here's the reason, right? So one can compensate the dispersion. So this is the dispersion management. So dispersion management, right? Dispersion management. So in other words, one can have two fiber with opposite dispersion, and they add together and compensate this. So for example, the ULT, right? So in a propagation length SL, let's do negative infinity, positive infinity, U0 omega, right? Then exponential, so it's the I over 2 and omega square, right? So we have omega square, and then K double prime 0, 1 times L1, and then we can have an add, right? I over 2 omega square K 0, 2 double prime and L2, right? And then minus I omega t, and then d omega. So now I'm writing an equation that includes two sections of fiber. First section, it has the dispersion coefficient as K naught 1 double prime times L1. And then the second equation, we have K02 double prime L2, right? K and K01 double prime and K02 double prime, right? And we have L1 and L2. And then minus I omega t d omega. right? So we have two component, and then two component, and then you will have the two component, and you will compensate dispersion. So hopefully this 2 will be 0. If this 2 will be 0, then I'll recover the original pulse in time domain back, right? If this was the combination was 0, then I get original pulse back, right? So this is called dispersion compensation. So meaning that it's the dispersion compensation, T-I-O-N, right? Compensation, right? Dispersion compensation. Okay, so it's the K not 01 double prime L1 plus K02 double prime L2 is 0. So we will add them together. It's going to be 0. So we will get the original pulse coming back, right? And we also know that J, I'm writing J as a subscript, so it could be 1, 2, 3, right? It's negative 2 pi c over lambda square K naught J double prime. So because it has the linear relationship between the D and the K, we can further write as D1 L1 plus D2 L2 equals 0, right? So now we need to construct a fiber, two section of fiber. Now they should have opposite dispersion sign, right? So in other words, first one will be positive chirp, second one will be negative chirp, and the amount will be the same. The positive chirp D1 times L1 equals plus the D2 L2 is 0. So the amount of chirp, they will be the same. So in the end, dispersion can be compensated. Any questions? Okay. Yeah. So I mean, I designed this course because this is either senior undergraduate student or graduate student, right? So you can tell that some of the problem I am mostly actually more designed towards research scale, right? This is mostly, I'm not actually trying to ask the problem, you just can directly find the answer from the lecture. Rather, you need to, observe and think, right? Okay. So if L1 equal to L2, then D1 equals negative D2, right? That's the dispersion. So if you also want to compensate so this is the compensation of the second order, right? So if you want to compensate the third order, right? Compensation of third order dispersion, you need to first compensate the K01 double prime L1 plus K02 double prime L2 is 0. And in the same time, you will write down the third order, right? The omega cube. So you want to write K01 triple prime L1 plus K02 triple prime L2 equals 0. Right? Okay. So that's the compensation of the third order. I'm going to show you more later on, but that's the third order compensation, right? Third order compensation. Okay. Any questions? Okay. I have some slides I'm going to show you, and then we will I will leave some time for our for the lab session. So some of you may still have some questions, and we will go over that. Okay, let me find my slides. Okay, let me find my slides, and that's the case, right? Okay, hold on. So let me share my screen. Let me share my screen. This is the, hold on. Share my screen. Okay. Click the button, share my screen. Can you all see my screen?
Yes.
Okay, thank you. Yeah, okay. So that's what will previous material. Okay, so now you can tell this is the figure intensity as a function of time, right? As a function of time. This dotted line is z equal to L. It's a nice Gaussian shape. If we have beta 2 as 0, so that means we don't have, there are different conventions, right? So some people write the beta 2, but beta 2 is the K naught double prime. Beta 3 is the K naught triple prime in our notation, right? So there's, as I explained in this material, there are people from the physics department, people from engineering, people from mathematics all working together, right? So you can see different notation in different materials, right? So just remember beta 2 is the K naught double prime, beta 3 is the beta 3 is the K naught triple prime. Okay, so when z equals 0 is a nice Gaussian shape. When z is 5 LD prime, right? So 5 third order dispersion length, that's what we got, right? So if we remove the second order dispersion, that's what we have. You can see the third order dispersion, the impact will give you oscillation in one side of the pulse, right? Because it's omega squared, cube. So it causes the oscillation in one side of the pulse. And you can tell also this oscillation is pretty deep, right? It is fully oscillate. It goes to 0 and then up, right? So we will see this third order dispersion very clear impact when second order dispersion is 0. On the other hand, if we make the second order dispersion and the impact of the second order and third order the same, the LD equals LD prime. So that means the impact of the second order and the impact of the third order, they are relatively the same. Then we have then we will get almost, we will see some oscillation, but we will also see some broadening, right? We will have some broadening, some oscillation. That means it's the combination of the second order and the third order. It's the combination of the second order and third order. So you can see this depth, right? Oscillation depth is not going to be 0. It's not as strong as the third order dispersion only. So it's the impact. In the same time, it has the broadening effect and it also have oscillation, right? So this picture in the lab session, you need to reproduce. Try to write the third order factor in the code and then make the third order z equal to 5 LD and make two scenarios. First one, beta 2 is 0. Second one, LD equal to LD prime, right? Okay. So that's the second order dispersion and third order dispersion. Okay, so this is another picture. It's showing this is evolution, right? This is the time. It's the T over T naught. right? T over T naught. So you should be familiar. It's the T over T naught. It's the super Gaussian M equal to 3, super Gaussian M equal to 3, beta 2 is 0, so there is no second order. The reason why we want to set beta 2 is 0, so we want to clearly see the third order dispersion, right? So we won't be impacted by second order dispersion. So you can tell this tail, right, has the oscillation. The depth of the oscillation is very deep to 0, right? Once you propagate up to 5 LD, it has very strong oscillation on the one side of the pulse, right? Okay, now let's look at this. So now when we talk about dispersion, right, that it will pass after the single mode fiber. It's called the single mode fiber, right? The pulse will be broadened. But one can design a so-called dispersion compensation fiber, right? It's the single mode fiber, dispersion compensation fiber. So I'll explain the single mode fiber later on, in later stage of our class. Once you compensate this dispersion, you can come back to the original pulse, right? Basically, this is the I K naught double prime omega z equals you add another K naught double prime omega z, right? So you can design different kind of fiber. Single mode fiber is mostly step index fiber. Now dispersion shifted fiber, right? Some kind of weird index profile. So now originally like this, now dispersion is shifted. So if our center wavelength is here, right? Center wavelength is here. One is negative, one is positive, right? So that can be compensated. And also we have so-called dispersion flattened fiber. So use some weird shape of index, your dispersion will be kind of flat, right? Dispersion flat, so that we can operate at this region, the dispersion all very zero, right? Dispersion all very small, actually very small, right? This is a dispersion compensated fiber. Dispersion compensated fiber. One can have some weird shape again. We can have very opposite dispersion, but one is greater than the way greater than the other one, so that we can use like 10 kilometer here, maybe just 1 kilometer of dispersion compensation. So in other words, this is usually dispersion propagating fiber usually on the ground. So you lay on the ground, for example, Dallas and Waco, right? Dallas and Waco, you use 20 kilometer. But in this in the central station, then you put a dispersion compensation fiber. Usually, this type of fiber is not lay on the ground. Usually, this dispersion compensation fiber is usually in the central station. Usually, okay. So that's the dispersion compensation concept. So why we want to do that? Let me actually let me give you a example, right? So this is the 40 gigabit per second, right? So that means each second we have 40 gigabit, right? 40 times 10 to the 9th bit, right? It's 1001 type of thing, right? Okay, so this will be 25 picosecond. You calculate the 40 bit per second. So this is transmitter output. That is the transmitting fiber. So after the transmitting, it has dispersion, right? It got distorted. Some frequency, longer wavelengths, it's going to be slow, fast, shorter wavelengths going to be fast. So if it's positive dispersion, this will be slow. The next negative dispersion, it will be fast. But no matter what, it will distort the pulse, right? I mean, you probably experienced that already. Once we have some dispersion, the pulse will be broadened. Of course, this is not that, it's actually pretty complicated. It becomes a weird pulse, right? It becomes weird pulse, yeah. So This is dispersion compensating fiber. Excuse me. So once we have this dispersion compensating fiber, we can compensate the dispersion. So in this case, the K0 double prime L1, K0 double prime L1, and the K0 double prime L2 is 0, right? K0 double prime. They are the same. So it's opposite, right? So the positive dispersion add negative dispersion add positive dispersion. And the length of these two is inversely proportional to the appropriate K0 double prime, right? Okay. How to add this dispersion? We can see that. So this is the transmitter. This is the receiver, right? Transmitter, receiver. So this triangle is the optical amplifier. So we can say optical amplifier, fiber 1 add the dispersion compensation, and fiber 2 add the dispersion compensation. So this is usually in the center station because the fiber, once you propagate, fiber got attenuated. We need to do the amplification, right? We need to carry out the amplification. And again, this is usually laid on the ground. This is between Dallas and Waco, right? So for example, this will be Dallas, this will be Hillsborough, right? So this will be Hillsborough, and then in between, and then we have the fiber, and then we got in between, right? In between, and then reach the end. This will be Waco. We add the dispersion compensator, right? Okay, so now we can see what is the dispersion. They add more and more, and then you compensate, and then your dispersion continue going up and up, and then be compensated, right? Dispersion will be compensated, okay? So we got the second case, we can first compensate the dispersion. And then we first become way negative value and then gradually coming up, right? Because this is a long distance. So you can think of this as 40 kilometer, this is 1 kilometer, right? But this 1 kilometer is in the center station. It's not laid on the ground. It's in a station. Okay, and then we, after this amplify, we got another one then going up, right? So another case is, so since we got very negative dispersion either here or there, right? So we want to actually have small dispersion and then go up, then big compensation, big. So in this case, we won't have actually very big dispersion anywhere in the fiber, right? So in this case, it won't cause some detrimental effect in the transmission. Okay, and just give you an example, right? So this is the normal dispersion fiber, right? So it's the real communication system is rather complicated, so you need to do a bunch of things. But let's focus on the fiber. So it's the negative 60 picosecond per nanometer per kilometer for 1 kilometer, right? And then we have propagation for 40 kilometer. And this is dispersion slope compensation. So it compensates when I say dispersion slope, that means K0 triple prime. When I say dispersion compensation, it means K0 double prime, right? I mean, but mostly dispersion slope, meaning that it's the higher order. Okay, so here's the picture. This is the initial pulse. The width is 1 picosecond. The width is 1 picosecond, right? And then after the propagation, it becomes 2.3 picosecond. But you can tell this is the very high oscillation in one tail, one side. That although the oscillation depth is not at 0, but we can tell that is the dispersion, third order dispersion dominant, right? Third order dispersion dominant. So in this case, if we compensate this third order dispersion, we will get this back, right? Excuse me. We will get this original pulse back. But in this case, it's not exactly original because you can there might be some high order effect involved. So, but it can obviously come back to 1.6 instead of 1. Okay, so that's it for today's lecture. I think we still have about 15 minutes left. We still have about 15 minutes left. I want to set this time for our, if you have previous questions on the homework 2. So, okay. So we will go back to the lab session. If you have questions, I can help you, right? Okay. Good.